Alright, so let's get started. I believe most of you are able to see this. In case if you are not able to see this, I am still recording it. I can repost it. This is the first time I am trying the YouTube live stream, and I hope it all goes well. So we will look at the 5 steps to write your own calibration verifier. So in many cases, when we start the calibration, before even we do the calibration, what we need to do is something called as verification. So we need a verification tool that let us verify whether the instrument is ready for calibration, needs a calibration, or we are okay with the current tolerance levels. So how we go about writing our own verifier tool? So in this webinar, we are going to look at using our own LabVIEW based tools to write a simple verifier that will test a multimeter and whether it is within the tolerance limits, and then if it is within the tolerance limits, it gives a pass or fail for different tests that it carries out, and based on that we can do a further tuning of the multimeter as we need it. So let's get started. By the way, I need to introduce myself in the first place. I'm Ajay and I'm the founder of Muckle.co, where we are helping the different manufacturers to automate their manufacturing line using the National Instrument platform, specifically LabVIEW and the test stand, and using the National Instrument hardwares. Okay, so of the first kind we are going to do with a verifier is to get an idea how the verification itself works. A verifier basically verifies functions, the various functions that any of your instrument will carry out. For example, if you take a multimeter can do a voltage measurement function, or it can do a current measurement or resistance measurement, so on and so forth. So you will go through the one after the other, and you will check if the measurements are within the specified limits. You would try to compare your measurement between your standard equipment, let's say digital multimeter with high precision, and you would also have some sources that will generate the necessary functions, either a voltage function or a current function that would connect, and you would compare against what your DUT, the unit under test, your multimeter, whatever the values it shows, is it very close to the standard that you have. If it is very close to the standard, then you say it's within the limits. So that's how the verification you usually do. And if the verified functions are within the limits, then you would say yes, it's good, and you don't need the calibration. You are okay for whatever it is. You leave it behind. There comes an additional uncertainty calculations and other details which we are not dealing at the moment, but we are keeping it much simpler in this video. If the limits are if the measurements are out of the limits, you would go for a calibration. in this case, you would try to calibrate it, you would try to fix something, change the resistor or change the capacitor or tune something to bring it within the limits. That's when that process is exactly the calibration itself. Once that is done, what you do again is you re-verify whether the calibrated the tuned items or bringing your changes within the expected limits. So you would redo the verification function for uncertainty calculations, and if it is coming back within the limits, you say yes, it's good now, it's good for going back to the production, going back to the use cases. If it again fails, even after trying for multiple times, after calibrating it multiple times, if it keeps failing, you would say no, this instrument is not good for measurement, and you would keep it aside. In some cases, you just keep it for a reference, just to measure only functions. But in most cases, you would not use it for production. So that's what happens. So when you look at this process, a verifier becomes a very important tool in itself, where you keep redoing the limit checkings very often, and it's also a time consuming if you don't automate that, if you don't write as something kind of a scripting to automate that. You do it before your calibration, after your calibration, you repeat it over and over as long as you bring it towards the calibration limits. In a calibration lab, you may not repeat it very often. You know by experience to what level you need to tune to bring it back. If it doesn't do, you do within a couple of verification, you decide, no, it is good, it is not good, yes, it is good now, something like that. So how this is going to give us? Oh yeah, I can stop the background music. Thanks for that. I hope it's better now. Do give me a shout if the background music is still causing any trouble. Thanks for bringing it up. So let's see, once you have this in place, you need to bring up a simple calibration verifier. What are the steps we are going to do? Before we even going to the steps, what we are going to use today to do the calibration is based on a LabVIEW tool, which is from National Instruments, and it is going to help us to write a verifier for ourselves that can allow us to redo this verification process over and over. Here is a link. I am going to put this up in the YouTube description later, that you can make use of it. This link is going to let you download a community edition that you can use for learning purposes. You can learn how to write your own verifier tool based on that. From these steps, you might need to get this downloaded and installed in order to do that. And what are the steps usually involved in doing any of your verifier? The basic steps that involves are, you need to come up with your own imagination or your own vision of how the tool should look like in the first place. You might try to draw up in a paper. I use an online tool like XCaliDraw, which allows us to draw something like this. I put up the different inputs that I want to get from the calibrator while he is calibrating. For example, in this case, I might want, for each of the different voltage set points, I would like to get what is the input value what is the set point in the first place. I might want the 1 volt test, 3 volt test, 5 volt test, 10 volts test, so on. And what is the UUT measurement that I might want? I put it down there. The UUT measurement is the actual device that is being calibrated, that measurement, and the standard measurement. The standard measurement, this is where it makes a little bit interesting in this whole process. The standard measurement, in many cases, we get a chance to automate. In this example, we are going to see how we have automated that. Either you can enter the UUT reference and standard reference, UUT measurement and standard measurement manually, or you can automate both of them. It depends on the case to case. When we take a simple multimeter, in many cases multimeter will not allow us to communicate directly via PC. We would expect that multimeter to be entered from the device input. I would need to enter, but in case of the standard measurements, I can connect my PC to my measurement device, like digital multimeter. When we take Agilent 6536 series, 36,000 series, it allows a direct communication. We can connect to that DMM and start receiving the data, what it is doing. So we are going to see one such example how it is done in this. So the standard measurement and probably some limits. Here the limits, I have kept it as minimal as possible. The deviation limit, like delta, DEL stands for delta. What is the plus delta I'm okay for? What is the minus delta I'm okay for? Between the UUT measurement and the standard measurements. For example, for a 1 volt set point, after all my resistance on the wires that connects between the instruments, I might be actually getting from the power supply 1.0001, some 0.1 millivolt extra on it. So from that 0.1 millivolt change, how much I would expect my UUT measurement to be, whether what level of variations it could be. I would enter there, and probably I would like to see the error before I decide whether it is a pass or fail. Based on these differences, I would get the error values, and these differences altogether will give me an idea whether my verifier is complete or incomplete. So this could be a sketch. This could be my vision of how the verifier should do. Essentially, this is what I would look for when I do my calibration. I would look for that specific different set points to be in that level of measurement from my device, UUT, in this case, multimeter. And if my multimeter is not in that range, I would say it's fail or it pass. It might pass in a specific range, and it might fail in the other range. So overall, based on this, I would also need to decide whether my overall result is a pass or fail. So once I have this step one ready, what I would do is, I have my idea what I need to do. Now it's time to go and start doing on the lab view side, the front panel side. It's a UI. UI stands for user interface. What I would do is, I would try to bring them all down into from the sketch. I would try to bring them down into a different input components in the user interface. An example of that user interface, I can bring it up here. So here is a LabVIEW project, and if I open the LabVIEW project, with this verifier, specific verifier. Here is a verifier. I can take it up to the next screen for a clarity. So in this verifier, I would do something like this. Um, I would go and drop the various input components that I might want. I go to the palettes and drop the control, the numeric control in the voltage set point and put it down here, something like this. And just like that, I would go and drop the other set points that I would need. For example, set voltage could be one of the value, and the next thing could be the standard measurement value in voltage, and the next one could be the UT measurement value, which is again in voltage. And just like that, I could add as much as I want, the plus and minus delta that I would do, the error values, and the result. The result could be a Boolean indicator. It tells whether it is a pass or fail. I might use the relevant controls or indicators as it works for me. So in this case, it could be something like this for true and false, and we can add a label on top of it to show it up. Finally, I would group them all together and put it on an array, a list of items, so that it can all be intact for the verifier. So I can group them using something called as a cluster and put them all down here and size horizontally, something like this, and finally put them all on an array where I can drop this and have as many as the list of items that I want. So that's how I would have brought up this UI with extra labels and extra overall verification results. So this would be the step 2, where you would drag and drop and combine all the various types of UI components together, and all those would start working together when you go to the step 3. If on step 3, this is the backbone of all those UI components. From your sketch, you have brought up your UI now, and then now you would try to connect all the different functions like DMM function and other functions in the back end of that. How you would do that is, even before we go and see how we do that, let's have a look at what's happening here. I can go to the code again and explain what's happening there. If we go to this VI and go to the coding part of it, when you go to the window and show the block diagram or give the shortcut Control E, that will take you to the block diagram where the whole functions are happening. So what is happening here? So when I run this VI, it is going to get a set of value of inputs, the standard voltages set points for that specific function, the calibration function, is going to be collected from here, 1 volt or 3.3 volt, 5 volt or 10 volt or 12 volt. And those values, when you look at here, it goes through the different blocks. Each of these boxes or different blocks where it sets the value to the power supply to ask for that power, and then wait for some stability in here, So it waits for some stability. It sets the voltage in the first place. It uses all the library VIs. So the little boxes that you see here is basically the library VIs for that specific power supply. It uses that and wait for stability, and then it goes for the stability is given for like 5 seconds here. It will wait in a loop for 5 seconds for the power supply to stabilize, and then it will ask for the user, us, to enter what is the value. Now I have set everything up. What is the value that you see on the digital multimeter? So one thing to notice here is we are expecting at this point, when we try to run, we are expecting at this point we have connected all of our hardware, our digital multimeter, power supply, uh, and the handheld multimeter are all interconnected with the supply voltages. And so when it comes to this point, it will ask us, what is the voltage that you see on your multimeter? And when it tells when you tell that's the voltage, it will use that voltage that you have given, and it will almost at the same spot as and when you have entered, it will try to measure from your the standard DMM, the digital multimeter, and calculate. So the multimeter that we have used here is 34465 Agilent DMM, and the power supply we have used is E36 series, 3600 series power supply. So now it has set the voltage, and it has waited, stabilized, got the DMM input, and also it got the multimeter input, handheld multimeter input. All it has to do now is it has to do the math around it, whether it is within the delta or whether it is out of the delta, and decide whether the specific set point is passing or failing. So it decides here whether the whether the delta is within the range, and it sets result as a pass or fail, and also calculates the error in millivolt, how much of the voltage is deviated from the standard measurement there. It just calculates that and puts up everything, and finally decides if overall it is as result is a pass or fail. It just summarizes based on all, if every step test point is pass, then it decides yes, it is it is a pass, the verification is a pass. If any of them is fail, it just decides it's a fail. If any one of them fails, it just decides it's a fail. And this loop, basically the outer box, what you see is a for loop, and all these steps is going to repeat over and over for all of your test points. For each of your set points, like here, for 5 of them, it is going to redo this over and over. You have set already the delta that you are expecting, and based on these two values, all other values are determined, and this is determined. Finally, once everything is done, it is going to generate a report. A report is a simple picture of what you see in your VI. It just takes a picture and gives you as a report. We will see that in the next slide how that happens. So when we go back, so this is the whole logic here, and some extra bits of code is there. Everything you can find from this link, the GitHub link, which is open for access. You can download it from there. So once you're ready with that, what could happen now is you would be ready to connect and run everything. So I have here a short video description, a video in fact. I will run it through and you would see how it works. let me check if you can hear my desktop audio. I hope you can now. Let me run that video. I have the digital multimeter, the standard reference, that is now connected to the triple output power supply, and this is in parallel is connected to the UUT, the instrument that we need to calibrate, Fluke 177, and the function that we are going to calibrate is DC voltage. It is set to DC voltage, and on the screen now we are going to run the calibrator verifier, and it is going to set the 1 volt first, and the input is going to enter. The input that we need to enter is from the multimeter reading, which is 1.007. So 1.007, hit OK. So that now reads from the standard and cross verifies and passes it. Now it goes for the next one, 3.3 volt, and for 3.3 we read it as 3.306, and that I enter, and it reads back from the standard reference and makes the comparison. Now it goes for the 5 volt. It sets the 5 volt and asks us to enter the value from the Fluke 5.005. I enter it, and it reads from the standard and cross verifies it. Just like that, it goes for the 10 volt set point now, and it asks what do I see from the UUT, that is 10.01, and I said OK. It gets recorded and cross verified. During all this course we see the error differences as well, and for the 12 volt what we see now is 12.01. So that gets recorded now, and the overall result is all verified, all cross-checked, and it's passed. Okay, I hope you can hear me okay now. So that was the verifier, how it works in Essence. So there was a lot of background noise. Apologize for that. It was recorded in a production environment. However, it has the overall coverage of how the run verifier works. So it runs through them. You basically have all these set points set in place in the first place, and then you would run them all together. So when you run them, it go one after the other, and when it goes through that, it just asks for each specific verifier and each specific set points, and it verifies that whether it passes or fails. So once that is done, once that is through, what happens is it has the final result logging, where it basically saves everything to a simple PNG file. So how that happens is so this VI, a little VI that we have connected in the end, that takes the image of your front panel and just generates your report straight away. It could be as complicated as you want, but this is the simplest form. Like you can have it in a CSV file or Excel file, or PDF file, in any format. But this is the simplest way that you can simply generate a picture of your VI that's ready with the calibration results. And that's how you could do a simple verifier. You can bring up a simple verifier based on these steps. Going back, so on the first step, we try to sketch our own thoughts how the verifier should come out. Then we try to draw the idea into a real user interface. We using all drag and drop items in the LabVIEW user interface. Then we do a backend logic that will allow us to connect all these pieces together, from the power supply to the DMM. Everything we will try to get connected, do the calculations here. And it's the time for a run. Between the step 2, step 3 and step 4, even step 2, step 3 and step 4, you might iterate for a little bit longer until you find it works. For me, for example, it took like at least 4 to 5 iterations before I can get it working. But these are the basic steps you need to go through to get it working. And finally, you would have the log results that's ready for sharing as the verification results. If you have any questions, feel free to put it up in the chat. I would be happy enough to give you any informations about how this whole thing stuff works. By the way, I will be also posting all those links and everything in the description that you can make use of. All right, I believe that that's a useful session. And again, I'm Ajay and I'm a LabVIEW expert, and I've been working together with a lot of manufacturing industry for getting their lines automated. We are also building a GageMaker, which is a calibration management tool, and this is something we are always interested to bring up to the customers. If you have any questions, feel free to shout us through any channel that you can find online. Thanks for watching, and hope you have a great day going forward. See you.